Hey guys, this is my first video from, well, not really being back because I haven't really been gone. I just haven't been posting any videos. So today we'll be talking about pure math, and within pure math we'll be talking about set theory. Pure math is an area of math, and set theory is an area of pure math. Pure mathematics is often stated to be useless and unimportant and overcomplicated, when I don't think it is. No, I know it's not. Pure math is very, very helpful for many things, though there are parts of pure math that are for the sake of just that we know it and it's just good for the brain. It's not exactly important, but there is still more things that are helpful than not. Now, pure math is my favorite of all the sciences. I like physics and I like all of the sciences, but pure math is my favorite by far because of proofs and mathematical and deep mathematical logic and all of that. I just found amazing. If you don't like pure math, you are boring. That is a fact. So, set theory. I'm gonna put something on the board. This definitely seen before. It's a bit wonky. This is a Venn diagram. But Venn diagrams are interesting because within set theory, it displays some simple set theory notation. But before that, I needed to explain something. What is a set? A set is a collection of elements or of a set, which we'll get to in another set. So, let's say we have some set A. Now normally you would put an equal sign, which means equals to, and then you would put square bracket, and then you'd write a list of the things that are inside the set. But I don't really like that. I put this equal sign with a C inside, which means this set A contains, and then what is over here. So you should do equals if this is for like a test, if you're doing, I don't know, something like that, because this is not a formal thing, but I just prefer to do this. Anyway, so we can have number 1, or you can even have like arbitrary things like the color purple or a triangle and stuff like that. We'll keep it formal, so just numbers and symbols. So 1, 2, and 4. Normally, most sets, order does not matter, but there are special types of sets which, with certain notation, are meant to be ordered in a specific way, but that's a bit more complicated, which is not for introduction. So, set A contains, or is equal to 1, 2, and 4. And the way you describe that these elements are inside A is also, you could do 1 is an element of A. This kind of weird 3/E is epsilon, or how you say it is an element of 1 is an element of A. So whatever is on this side is an element of the set that's on this side. So there's also another thing where, let's say 0 is not an element of A. There's also something else which isn't exactly in set theory, but is to do with mathematical logic, something called implies, which is an arrow, and then let's say if you have 1 implies true. 1 is set to be true, 0 is set to be false. This is a little bit complicated, but you know what? Why not? Some of you are smart. Some of you. So let's say we have -1 is an element of A. These are meant to be curly brackets for like an argument. An argument is like this sort of thing. This is how I do curly brackets. And then you put this implies false 0 because this is not true. But normally you would normally put this sort of thing, yeah, because this is for like proofs and all that. But anyway, So 1, 2, and 4 are part of this set. And remember how I said sets can be a part of other sets? So let's say we have some set Z, which contains 1, 3, A. An important thing to know about sets is they cannot contain something more than once. Like, I couldn't have like another 1 here. That is impossible. It is not allowed. So 1, 3, and A. And from this, we then know that A does not contain 1 or 3. I'm pretty sure. Yeah, I think so. And there's also something called the cardinality, which you would write as 2 vertical lines. And then inside here you would put your set. This is equal to some integer, or 0. So that tells you how many things are in the set. So it would be kind of like this. Let's say a set is a box because of these box brackets. You have a box, and that A is also a box, but it's also closed. So you have a box that you open, there's a 1, a 2, and another box. How many things are in there? 1, that's one thing. 2, that's the second thing. And another box, that's 3 things. So the cardinality of Z is 3. Cardinality. I'm pretty sure that's how you spell it. There's also something called the empty set, which is the set that contains nothing. And every set that contains nothing is the empty set. Like if you have A equals, contains, and C contains, A is equal to C. They are the same. They are the empty set, which is like a 0 with like a line through it. It's not meant to be this oblong. The empty set contains nothing. You would say the empty set has a cardinality that is equal to 0. It is equal to nothing because it has nothing inside of it. Now, what if we had some set Q that contains 3, 0, 2, and the empty set? How many things are here? So that means we need to find the cardinality of the set. What is the cardinality of Q? I've got to say at the start of the video, this will be one of the videos which you can kind of like answer if you pause and stop. Cardinality of Q is 4, because we have 4 things inside the box or the set. 3, 0, 2, and the empty set. The empty set is now just an empty box, but it's still a box, which means it itself is a thing which can be counted when counting for the cardinality. You could also write it as like another set of brackets if you wanted, but just to make it a little bit more simple, like that. Now, back to the Venn diagram. The Venn diagram represents something called the union, and the intersection of a set. The union is like this. So we have 2 sets, A and B, and then you do this kind of like big U. This is union. So think of it as kind of like an and symbol. A and B is equal to, so that means what are the elements that are in both A and B? And you'd write it as like this. So you could do it with 2 circles, like the Venn diagram. That's A, that's B. Let's say A is equal to 1, 3, 5. B is equal to 1, 4, 6. So let's say this is B, so we put 1, 4, 6, 1, 3, 5. But we need to cross 1 out from both sides. Since they both share it, and that means you put it in here. Since they're crossing over, it's the union. Both of them have it. So the union of A and B is 1. This is different from like a cardinality. You could also, if there was multiple, you could also find the cardinality of a union, because this technically creates a unique set. which is equal to, in this case, 1. It's the cardinality of the set is equal to the element of the set inside. And so I remember when I said the intersection is the things that aren't in, I think, is it either? Yeah, that aren't in either set. Yeah, that aren't in one or the other. Yeah, aren't in either set. So the intersection of A and B could be like 0 or I. This is the intersection. And these are just the individual sets. So this can be every single value except the values that are here. You can, there's another thing, but this is a little bit complicated, but I'll still say it because why not? You can also, I did create this function in a way, but it does exist in some form. Now that's cond, which means shortened from condition. You could write some condition which applies to the sets, like the elements in the set must be multiples of 2, or something like that. So, A element B, A, wait, yeah, A, say for A to be an element of B, A, actually we'll do it like this, A over 2 must be in the natural numbers, meaning if you divide it by 2 and it's even, that means it would give a natural number. But if dividing by 2 and it was 3, let's say 3 divided by 2, it gives you 1.5, that is not a natural number. Let's say we have A, which contains 1, 3, 5, and 8. We have some set over B, which contains 3, 6, 7, 1. What is the cardinality of the union between A and B? I'll give you a sec while I just find my drink. The cardinality between the union of A and B is 2, because they both share 1 and 3. So that means there's 2 objects, or 2 things in that point that they cross over, so cardinality is 2. Also, this is complicated, but this is still helpful. This looks a bit scary, but I'll read it. So, any arbitrary set, arbitrary is random, but just a better word for random, because technically nothing is random. Any set union with any other set, and you find its cardinality, must be greater or equal to the cardinality of the smallest set. So the smallest set out of the 2, its cardinality is the lower bound for what the cardinality of these 2 must be. So if S1 is equal to 1, 2, 3, S2 is equal to 1, 2. Since this has 2, that means this is the minimum that it could be. It can't be less, because that means it would be removing an element, which in this instance, that is not what's happening. That's not meant to be 123 or 12, that's meant to be comment that way. Also, A, so, okay, that pen's not working, let's find out. A does not contain A. As in, A is not an element of A, but there is an exception. That is in the set of all numbers. Think about it. If the set of all numbers that contained every number, the set of all sets that contain every single set, and since it itself is a set, that means it should contain itself, and it does, and that's one of the, there is some other instances when it can work, but in normal standards, A cannot be in A. A can be equal to A, but A is not in A. We can have this. I think if you have A is equal to the cardinality of A. Since the cardinality gives us kind of like a unique value. So since A just contains one thing, that means this would be 1. So that means A is equal to 1. Here, it gives the value for you, which is kind of a cool thing, isn't it? You could also, I think that's one of my favorite things that you can do, where you can have some set which equals the cardinality of this set. But there's something you might notice if you know this in maths. There's something called an absolute value, which is the same symbol for cardinality, but they mean different things. Just to clear that up, they're not the same. Let's say we have K is equal to, no, this, can you tell me why this is wrong? Why this shouldn't exist? The reason why it can't exist is because this is the cardinality of K. The set K has 1, 2, 3 things. If you put 3 here, that would violate the rule of a set cannot contain more than one of like something. It can't have a double or a triple or anything like that. So this, also, when, you know, with the implies, where I have implies 1 for true and 0 for false, this isn't true or false. This is, what I do is a C, implies contradiction. That means paradox. Doesn't work. Silly. So let's say you remove 3 and replace it with 4, it would work now, because then it would be 3, 4, the empty set. That's meant to be the empty set, not theta, which is equal to K. Now, you may be wondering, how do you like describe, using mathematical set theory terms, adding or taking away from a set? You wouldn't use plus or minus, but I'll show you. Let's say we have A. This is saying that we add A to the set B. And let's say we have, and this is A take away B. So if A is an element of B, you could write this to take it out of B. So you could, example, say B at the start is equal to 1 and 2. Now B is equal to 1, 2, 3. Or you can write it as is kind of how you would like do it. Obviously a little bit more complicated than this, but it's separated by these black bars. So B at the start is equal. Actually, what was the B contains 1 and 2. Then you add 3 to B. B now contains 1, 2, and 3. I forgot to add the square brackets there. Now I'm going to give some questions. What is the cardinality of set A? So, set A contains a set which contains 0. The cardinality of that set is 1, but that's not important. So, since there's only one set there is only one thing in A, that means its cardinality is 1. Set J contains these elements. What is the cardinality of J and what does this imply? J contains, J contains 3, -1, the square of the cardinality of J, and the empty set. Thus, its cardinality is 4. See, this was just a little trick. This isn't exactly important unless, since there's 4 items, that means this would be 4 squared 16. If it was, let's say, only 1 item, and one, if it contradicted itself. And for implies, you would put 1 for true, so for this, 4. That is all for now. I don't really have too much to say of introductory set theory. It does go in more in depth. And, actually, hold on, before I make that mistake again. There are sets other than the empty set which have specific names. I remember me doing that weird kind of V/N. This is called the natural set. Natural, that's a horrible thing for natural, which contains the natural numbers. And actually, if we have Z with like a bar, Z stands for what gives integers, so non-decimals. So I, 3, 4, 2, 6, 4,268. Anything that is not a fraction or 0. I actually think no, 0 is an integer. Infinity, I don't think is technically. Infinity is and isn't a number simultaneously. So actually, with special sets, because of its set being defined and not changeable as it is, you can use that to build arguments. So A is an element of B. A is an element of the integers. B equals 1/2 0, and 3. Which one of these 4 numbers can A not be? A half. It cannot be a half since A is an integer. Oh yeah, by the way, you can put like halves as. But yeah, I think that concludes it for now. I will make another video on set 3 that goes a little bit more deeper in, but so far I think I've told you really anything that's exactly relevant. One more actually no, not one more thing, because I'm going to make I think I might make a video after this about the function that I made called the delta function, but I'm going to change its name to the downward function. Plus I've done some work on it that's very interesting. But bye and stay curious.